Okay, and a good morning to everyone. And I'm told that we were listening to Journey, and see, I'm supposed to do this, Open Your Arms to Algebra. Okay, I'm sure that was the full title. So tell me a little more about Journey. Is anybody, I don't know the group, so.
Well, they're not together anymore, I don't think.
Well, then that means they're at least a year old.
Oh, no,
They used to have this guy named Steve Perry singing lead, and now they have another guy that looks and sounds just like him.
Really?
Wow, really?
Okay.
Yeah.
Well,
Where's Steve Perry then?
He went solo
Went
and
solo,
when
right.
Solo
he
went
went
down.
one-hit wonder.
Yeah.
Okay, so one of those situations
Well,
where...
they were the late 70s, 80s.
Right.
Okay, it's just a group that I don't remember hearing. Now, I'll ask Sarah that. She'll say pretty much the same kind of thing. Could have just said, give me the lead singer and who did what and where they are now. We need Jeff this morning, right?
Yes.
Jeff can tell us who the drummer was and the bass and so on. Okay.
Probably.
Now, we are working with parabolas in this set of problems we just did. And at least the early comment was the parabolas are pretty good. What about adding and subtracting polynomials? That's pretty comfortable? Anything we need to look at in the homework to spend any time with that?
Up the problem like on 37.
Okay, can you give me the page number, please? So 37 is the problem, and one of us is going to find the page. Is it 231? Okay, so 231, let me get the problem up here. And we want the value of the polynomial as we have a 2x to the fifth, all the way down to an x squared. It's a fifth degree polynomial, and we are wanting a value at 2 and negative 1. Which part is it you would like to see?
The second part.
The negative 1?
Yes.
Okay.
I couldn't get the negative sign.
Okay, that sounds like a parentheses problem, but we'll see. So could you, Debbie, put that up on the board just a minute more, not a minute, a few seconds, so I can get it written. So we have 2x to the fifth, and I have a minus 4x to the fourth, and then I have a plus 5x cubed, and I have a minus x squared. And then I want let x equal negative 1, correct? And this problem really is a matter of watching the signs, because you have to be careful to put the minus 1 in parentheses. So your 2x to the fifth, you put a 2, you put the minus 1, you place that in the parentheses, and that's what's going to guarantee you at that point you have a negative 2 for this portion. Because an odd exponent with a negative number inside is going to be a negative value. Okay, then I have minus 4 times x to the fourth, and because the minus 1 is to the fourth, it's going to be a positive 1, so that's again going to give me a negative 4. My guess is the problem may be associated with not using parentheses, but I can't guarantee that. Now, plus 5 times minus 1 to the third is going to give me a negative 5, then minus, and this is the one that really may or may not be unsettling to you, but this comes out negative 1. So it appears I have everything with negative signs at the end, and so I have a negative 12. But this is one of those little cautions that they write about in the text, where place the value in the parentheses to make sure that you don't get trapped on a sign in the evaluation. You're welcome. I'm going to use a little different notation here for a moment, just so you can see it for the first time. We could argue that this is a polynomial and say, use the letter P for polynomial. And so I could argue that P of x is equal to this expression. So it's just a little bit of a notation. And what I'm being asked to find here is P of negative 1, and that then tells you to substitute the negative 1 for x. And that notation is a very important notation as we go along. Now we refer to this as a polynomial in x. So P of x is the way you say that. P of x. And if you want to have the polynomial evaluated at -1, putting p of -1 says substitute for the variable the -1. Any further discussion in that one? Any other questions? Going around the room looking for questions. If not, would you be kind enough then, please, to make sure your name's on the paper and pass it forward. While that's going on, the request has been made from several people who are watching the videos to again announce where and when for the exam. For you who are in here, in this class on campus, the test is Friday at our usual time, 10 o'clock, but our room is going to be Founders Hall 123, like Lotus, 123. Founders Hall 123. For the group who are doing the videos, the test is on Saturday, same time, same place. Founders Hall 123 on Saturday. But here's an announcement that came out of something that was a bit of brainstorming, answering somebody's question. If you are watching this as a video course, organize all your homework from the first 4 weeks chronologically, have it in a binder, all presented, and this is just for the people who are on the video base. Bring it to the test with your name in the folder or binder, and I want to take a look at what you've done for the 4 weeks. So I want all the homework that has been done organized in a binder, by date, assignment, so I can see what's done. It'll give me an idea of whether you're blowing smoke or being serious. So that's my announcement. I will be sending out response to emails probably this evening from people I've heard from saying the same thing, and it will be an interesting indication of people who are watching to see if they are really watching, if they do come with the required materials. And another, by the way, you need a blue book. So blue books for the test. Most of you have, of course, been here to hear that, but a blue book for the test, it's a small version, and you will need that for the test. So with that said, and we've got the homework passed forward, where is the, okay, it's up here near the front. Okay, thank you. And just let me pick up that. I appreciate it. Thank you very much. And a new section. Products, meaning that we're going to multiply, and we're going to look at exponents. So I'm going to look at a problem that we're all familiar with called place value in our base 10 number system as a start for this, and use that as a spin-off because it then gives us some ideas of why we are going to create some rules, as they are called, for exponents. So, in a sense, we see a little bit of that here as we come back, and so much for my telegraphing where I'm going, Debbie. Sorry about that. But we have a -1 to the 5th, a -1 to the 4th, a -1 to the 3rd, a -1 to the 2nd. Well, that's a little bit like what happens if I take this particular number. And this is not as random as it may seem. This is the number of cubic inches in a cubic foot. So if we have a block of ice, 12 inches by 12 inches by 12 inches, and you think of making 1-inch cubed ice cubes, you could get 1,728 ice cubes from that block of ice. I don't know of anybody who's ever done that, but that's the idea. Now, this is a base 10 number, and so we all, I think, the assumption is, are comfortable with doing place value, and I'm just doing it with exponents. So we have a 10 to the 3rd, 10 to the 2nd, technically a 10 to the 1st, and this is 10 to the 0. In the same way, and again, I'm doing this not so much as familiarity at this point, but let's say that you saw a number written this way, And you might argue that's just a silly looking number. But if you're in the computer world and you think of base 2, then you need to understand that these switches, which are in an on-off position, so the 0 being off, the 1 being on, are still referencing place values. So this one still is the 1's place, but the next one is your base. And that's always the case. So we have a 2. And then the idea is that when we're in base 2, we multiply by a 2, just like in base 10, we multiplied by 10 as we went in this direction. Well, in base 2, we're going to do precisely the same thing. So you argue the next place value is 2 to the 2nd, then 2 to the 3rd, then I'll bring this one down a little bit further, 2 to the 4th, 2 to the 5th. I'm sort of alternating positions so I have room. 2 to the 6th. You just multiply by 2 each time. So the notion here is I could argue that 1 is going to be 2 to the 0. So I have 2 to the 1st, I start with 2 to the 0. Notice the exponents stair step upwards, just like they did here. 10 to the 1st, then 10 to the 2nd, 10 to the 3rd. And whether you're doing it in base 2 or base 10, there's a very obvious thing going on here. If I multiply 10 times 10 to the 3rd to get the next place value, you know it's 10 to the 4th. But the important issue is 10 is the same as 10 to the 1st. And so what you realize is that that is the same as adding the exponents to get the new exponent, 10 to the 4th. So that becomes just an observation. And it also works with the powers of 2. I had the last power I wrote there as 2 to the 6th. If I want the next place value, I multiply by 2 to the 1st. We know that's going to be 2 to the 7th. But notice again, I do what? I simply add the exponents to get my answer, which is 2 to the 7th. So the argument, and I just went through this argument in Math 10 about an hour ago, because we were looking at this same kind of problem, and I was making the observation, planning ahead to the algebra course for them, that if I had, instead of a 10, just some base, b, that if I had the base multiplied by base to the 3rd, then to generalize what happened here in these two bases, I would just argue that I would add the exponents and get b to the 4th. That's a generalization. Doesn't matter what your base is. You are, in essence, increasing the exponent by 1 as you go to the left. Well, there's nothing sacred about the 1 and the 3, or the 1 and the 6 I had right here. I could argue the same thing if I took b to the 3rd times b to the 5th. Now, of course, what's clear here, you would never do this in place value because you always multiply by b to the 1st. But in the same way, I'm going to do what? Just add the exponents and argue that I now have b to the 8th power. That can become a statement then for any exponent I have. So if I'm going to do it in that sense, I could argue as a generalization now, if I have b to the m power times b to the n power, and I hope that looks a lot like a 6 to you, that helps. Seeing 6's instead of b's, same argument. Then this is b to the m plus n, and you have a general rule. That's a multiplication rule. When the base is the same, and if you don't like the letter b, you could say x. And now it's really algebra. So if I have x to the m, and would you write now an x for your multiplication? You'd write times x to the n. You might use a dot to signify the multiplication, but then in the same way you're going to say what? X to the m plus n. Now there's an obvious question here. Is the exponent always positive? Otherwise I have an m and an n, and the illustrations I've provided suggests the exponent is going to be a positive. But if you've done some pre-algebra and you think of what we have in decimals, looking at place value, same argument now. If I take, and instead of having the decimal at the end for 1728, have it in the front. So here's the number, 0.1728. What is my place value to the right? Well, I divide by 10. So this is called the tenths place, which is 1 over 10. Then this becomes what? The 1 over 100, and so on. Now the question, if I'm talking about exponents, remember I went 10 to the third, 10 to the second, 10 to the first, 10 to the 0. If I'm thinking of the place value as I go this way now to the right, and Debbie, could you for the moment give me with camera 1 the 1728 that I had, and I want to talk about that just for a moment. Look at the pattern. The 3, the 2, the 1, the 0. If I keep subtracting 1 each time, and I think of the decimal being here, your next place value to the right is 10 to the minus 1. And so we argue, now we're going to go back to the other expression, we argue that 1 over 10 is the same as 10 to the minus 1. And of course, 1 over 100 is the same as 10 to the minus 2. So we make a definition. And I just want to, as a kind of, we do this in Math 10, and so I don't know to what extent it's being done in 20, but just to understand that exponents can be positive or negative. And the question is, what do we understand for 10 to the minus 1? We understand that means 1 over 10 to the first. If you have a 10 to the minus 2, you interpret that as 1 over 10 to the positive exponent. So if I had 10 to the minus 3, it's going to be 1 over 10 to the third. And so the point being here, and we need to see that 3, I didn't do a very good job of using my space. But that's going to be a definition for a negative exponent. I just want you to understand that this first statement we're making here about x to the m, x to the n, and then we just add the exponents, even if they were negative, it still works. Same argument works. Okay, so that's the product involving an expression that involves two monomials multiplied together. We would call this that infamous simplify. Remember, it's sort of a generic phrase that means you're in trouble. Simplify and your life gets more complicated. So simplify here would mean add the exponents. So I'm going to leave that on the board there for a moment and just look at that product rule in its usual form, and with due, I guess, acceptance. I'm not real pleased, but this is very typical. Let's go to the book. I'm on page 235. Okay, so we're on page 235. And note, instead of using x to the m times x to the n or b to the m times b to the n, we're using a to the m and a to the n. But it's general. That's very typical. And I just realized something I made a commitment to doing that somebody requested, and I realized I just blew it, managed to blow it in the first 20 minutes. Somebody asked if I would try each day to let people know where I was going to be in the text, so that somebody could have the text open and know where we were going to be as the presentation's being done on the video. So with due apologies, but we are on section 4.2, page 235, and that's where we'll be focused for much of the time. So this first rule we've already done. And then the question, are there variations on the rule? Now, so far, I've been able to use the idea of number base to generate some interest in what we're doing and maybe to give some understanding. Some of the next parts are not quite as obvious. There are other variations on this. And the first one is page 236, and this doesn't come naturally, a to the m to the n. So you have a to the m quantity to the n power. And our argument is going to be that multiply the m times the n, and that's your new exponent, a to the mn. I was thinking of that movie that's pretty much considered one of the classics now with Sidney Poitier, Lilies of the Field or something like that, and they sing Amen. So this a to the mn, a, anyway. You might think of that movie as you watch that. I know that's reaching for things. That's sort of a trade-off for Journey.
You're talking about this power rule?
On page 236. It's called the power rule.
That's right. Okay, sorry.
Like a power bar.
All right.
You're more powerful having this rule. Okay, now we're going to look at that, and I'm looking at space. So Debbie, we're going to be over to the sideboard and anticipating what I'll do after that. But the argument here in this a to the m to the n is you're just going to multiply the exponent. But you've got to be very careful, because it's like, okay, we have one rule, now we have two rules, then we're going to go to 3 rules, and then to 4 rules, and it's a little bit like juggling oranges. The first couple rules you can juggle in your head without too much trouble. Then you get to your 3rd orange, and what often happens? Everything goes on the floor. And even if you got 3, by the time the 4th comes, it's amazing. We went to Cirque du Soleil. I'm not probably pronouncing that well, but in San Jose. And they had a juggler doing, I think, 5 at a time. And if you've ever tried juggling, 5 at a time is impressive. And that's what we're doing today. So let's look at the 3rd orange. Back to the document cam. Here's another variation. A product of AB quantity to the mth power. And notice how we bring the m across. So we bring the m across and say a to the m, b to the m. So we have 2 different rules, and let's see if I can write them in a typical way. This is the first one, so we have a to the m to the n. And so we're arguing this is what? A to the mn. But if you have a times b to the m, we're arguing that that's a to the m, b to the m. And is there anything similar in those? Well, in a way, a is a to the first. B is b to the first, correct? So in that sense, I'm doing what with this m? Multiplying it across like a distributive property. I'm saying m times 1 and m times 1. Okay? So if I put these 2 together, let me show you what I have in mind. A to the 2nd, b to the 3rd, all to the 4th. Looks a little different form, right? So that would be a to the what? 8th, b to the 12th. Because I'm multiplying this 4 across both exponents. And that's not very clear from what I've written here in this statement, but that's implied. Now, another way of seeing this is the following combination. I have a to the 2nd to the what? The 4th, b to the 3rd to the 4th. You see how I'm using this first rule, doing it this way? Okay, it says, whatever a is, I'm taking it to the nth power. Whatever b is, I'm taking it to the nth power. A happens to be, in a sense, a squared. And b happens to be in the form b cubed. So now I'm taking a to the 2nd to the 4th, which is a to the 8th, b to the 12th. Any question there? Okay. Question? Wait, there'll be more problems that you can ask, I think. I'm going to leave that up there for a moment, Debbie, and I'm just going to go back to the document cam because I'd like to slide now to the next rule. Now, there's a little caveat on this one you have to be careful of, and it says the denominator cannot be 0. So now we have a over b quantity to the mth, and we're saying it's a to the mth over b to the mth, b not equal to 0. So as I catalog this new one, I have a quotient of a over b, the entire mess, to the mth power. And I'm arguing that that's going to be what? A to the mth over b to the m power. And again, I could have a rather convoluted combination of the first and third, because I could have written, much as I did here, I guess with the a to the second, let's say I had a to the second over b to the third, all to the what? The fourth power. Now what's your argument? Well, you could say it's just a to the eighth over what? B to the 12th. That's how I would be inclined to see it without writing anything. But if you're going to use the three different expressions, you would probably first write a to the second to the fourth over b to the third to the fourth, which then gives you a to the eighth over b to the 12th. So we're putting pieces together. The restriction, whatever you have in the bottom cannot be 0. Why? What's the argument? You cannot divide by a 0. Okay, so I'll leave that one there. And most of this is fairly obvious in a way. It's when you start pulling it together that it may not seem quite as nice. But let's look at the list together on page 238. Here are them all written at the same time. And that seems to read okay in the screen. I'm hoping it's going across okay as we stream that out. Those are 4 rules you need to know. Knowing the rules isn't the hard part here. What tends to be harder is applying them and not get some silly mistake in the process. We have some fairly straightforward problems, but it's when you start getting a mess such as what I now have on the screen. These are from examples on page 238. Suddenly, this is part C that I'm looking at on 238. It's example number 6. Putting it all together at one time. So we're going to work this one out together, and then we're going to look at some of the problems given in the exercise. But as you look at it, what do you see first thing you have to do? In fact, it's even color-coded for you. I mean, there are times I think color gets used a little bit more in these with blues and reds and greens and yellows. But the 4 and the 3 are the critical, because you have to bring those from outside the parentheses inside. Now, I don't think you're going to have trouble seeing x to the 8th, y to the 12th. But you might not see 2 to the 4th because there's not a 1 on that 2 as an exponent. So that's my concern. Now let me see if I can get this page blocked in a way that'll keep it flat enough that it won't. That's not bad. Let's go with it, Debbie. Now, it's the little things. And this is where algebra, in its unforgiving kind of demand for detail, that you can lose it very quickly. The first thing I'm doing, while Debbie's patiently waiting for me to finish, is writing the problem. 3x, y to the second, and now to the third. Okay. First recommendation, when you don't see an exponent, write it in. What is the exponent you're not seeing? Okay, there's a 2 to the first, correct? Where else? 3 to the first. That one step can be the difference between a correct problem and an incorrect problem. The second x. Thank you. I didn't pick up on that yet. Good observation. The second x on that second parentheses needed a 1. Now, if you have exponents everywhere, what will be easy to see? Multiply through on the exponent. So that's going to become 2 to the 4th. Now the question, do you need to see that as x to the 2nd to the 4th, or can you just see it as x to the 8th immediately? I hope maybe at this point you see x to the 8th right out of the gate. And in the same way you see y to the what? 12th. But what will be the danger in misusing a rule? What's the potential danger here? The first rule said that if you had a to the m times b to the m, you added the exponents, correct? So there's going to be a temptation. Sometimes you add, sometimes you multiply. Remembering which to do when is a little maybe more confusing. So to that extent, it might have been to an advantage to write y to the 3rd to the 4th. So you could have done 2 to the 1st to the 4th, then x to the 2nd to the 4th, y to the 3rd to the 4th, and then gone to this as your next step. Right now, my guess is this seems overkill. Immediately from here to here without this. But if you start making DAEs, dumbass errors, the careless stuff, the thing that you just didn't think you'd do, then do what? Take the time to be more detailed. Then back off from it and try to pick up speed again. Okay, so what is this going to become? 3 to the 3rd, x to the 3rd. Ooh, you nearly did it. You nearly did what I do. Namely, you saw 2 and 3 and added and got 5 instead of multiplied and getting 6. Those are those little errors that in your mind you know you should multiply and yet you add. And there's no way of getting around it other than sometimes verbalizing, and you say it and then you hear yourself saying it. And it gets very difficult if you have 30 people in a room all saying what they're doing. And so people get disgruntled in a test environment. What is the alternate here? To actually write out 3 to the 1st to the 3rd, x to the 1st to the 3rd, y to the 2nd to the 3rd. Then go to this as a step. Now once you get here, what can you do? Well, you can rearrange, and I don't know if it's necessary to say, well, gee, I have 2 to the 4th times 3 to the 3rd. And by the way, that's not 5 to the 7th. Okay, it may seem reasonable and logical, but there's nothing you can do there short of saying 2 to the 4th is 16, 3 to the 3rd is 27, and the danger is going to be seeing 2 to the 4th as 6.
Can you put like brackets?
You could. That may help, like this, parentheses around them.
Oh, no, the second step.
This one?
The second step.
This step? This step?
Yeah.
Like a bracket here and a bracket there? Yes, if you want to still keep those separated. You didn't say parentheses, so I'll go with the brackets you argued. Yeah, you could do that if that helps clarify. But you still at some point have to do what? Rearrange. Now here, when you get to the x to the 8th and you have x to the 3rd, then y to the 12th, y to the 6th, is that step a necessary step? Good point. Not unless you need it. If you need it to keep from making the careless error, do it. But it's not an obligatory step. Okay, this, again, I'm going for the tedious, show every step kind of solution. But my hope would be that you would be able to see that as simply x to the 11th, y to the 18th immediately without doing that. Now what about here? Well, I'd probably at this point write 16 times and probably do a parentheses, 27. I don't know at the moment what the text wants you to do here. Do they show it expanded out with the numbers?
Yeah.
Okay, so we have 16 times 27, which is going to give me a larger number to write down.
432.
432? Thank you. Then x to the 11th, y to the 18th, and do you get the feeling that you're having to do more than you need carrying it out to that detail? But it does keep you maybe from making the careless error. Bottom line, you've got to pick up the pace to where maybe you can go from. Let me show you the way I would like you to be able to do this, is to go from here. Let's see. I didn't do that right. I want an arrow, which steps I want you to be able to do. Maybe a check mark would be better. You start here, obviously. Then in a way, I'd really like you to be able to go there next, and then maybe immediately down to here. Only because the 16 and 27 you probably aren't going to do in your head. But maybe 3 steps from here to here, down to here, and then finish it off with the multiplication. That's where you're going to have to be in a test environment. Quickly in your head and not make careless errors. But there are so many places to get trapped. And the problem is, the more focused you get, the more easy it's going to be to leave a step out or make a careless error. The most typical error was right up here. If you don't write that 2 to the first, you're likely to not get 2 to the fourth. You'll easily get the x to the 8th, the x to the 3rd, and so on. But you may not get the constants. We'll leave that there, and I want to go to another problem and look at it. Only because this last problem now brings up something that was addressed in an earlier question where we evaluated something. What's your difficulty here that's being introduced? The negatives. Okay, and as we look at this one, again, the question, how can you avoid some of the traps? I'm going to write the problem first and then talk about it. And I think you can see one place that I'm going to probably amend what I have here. And then I have a y to the 4th, to the 3rd. What would be the first thing you think I might do? The 1 with the y. Good. Now, do you remember a way of dealing with the negative rule on a sum if you have a minus of a plus b, and we said it's minus a minus b? But another way of looking at the minus sign outside of parentheses is a what? Negative 1 as a coefficient. So if I wrote this as negative 1 times x cubed y to the first, and this is negative 1, you see where I could treat that negative sign as a value, and now maybe it becomes a little more obvious that I have negative 1 to the 2nd, x to the, well, I'll do it this way for a moment. I'm a little bit reluctant in a way, but it's maybe better to show it. And I'm going to talk about how you can avoid this step in a way. And there's a time to be very detailed, but at some point you do have to let go. Now the minus 1 to the 2nd is a what? A positive 1. So this certainly, in a way, forces me to deal with, I had a square of a negative expression. So you could have argued, if I have a minus something here and I'm taking it to the 2nd power, my result's going to be positive. In the same way with a negative here, to the 3rd power, the result's going to be negative. That's one way of dealing with it. But here, you can avoid the thought process in a way, sort of sidestep the issue, and argue, well, that's just a plus x to the 6th, y to the 2nd. Now what about here? That's a negative 1. So maybe back to the bracket suggestion for the moment. And then x to the 15th, y to the 12th. Now, if I have a positive expression times a negative expression, it must be negative. And then maybe, for the moment, we can jump to this. And we're just one step away, minus x to the 21st, y to the 14th. And remember, that's negative, that expression, that factor, or I should say term, it's the additive inverse of x to the 21st, y to the 14th. Is this necessarily a negative number for all x and y? The answer is no. If I have x as a negative number to the 21st power, we'll make it negative, and I'll have a negative, which will make this ultimately a positive value. We're back to this question. Is negative x negative only when x is positive? If x is less than 0, negative x is positive. So my point down here, this whole expression I have now as a single term, because it involves a product, is going to be both, well, there's both possibilities. It can be negative, it can be positive, it could be 0. By the way, what is the degree of that term? 21st is a very good wrong answer. It's not 21. What is the degree of the term? Not 21. Not 21. 35th degree term. What are you supposed to do to get the degree? Add the exponents on the variables in the product. Since I had two variables in the product, this is a monomial in two variables, and it is a 35th degree term. Not just the x. Again, I made a comment to you yesterday that this is the equation of what conic section? xy equals 1. What conic? If I do this for you. Let's see, get so in camera. Okay, hyperbola. Good. This is the hyperbola, as opposed to the hyperbole in English. The hyperbola. What is the degree of that term on the left side? The degree of this term. It is 2, because the exponents are understood to be 1s. Those are the unseen ones. And I add the two 1s, I get 2. This is a second degree term on the left side in two variables. Okay? Pam?
Okay, so if that was actually negative x to the 21st plus y to the 14th, it would be a 21st.
Okay, the question is, if, contrary to what I have written on the board for the moment, so this is just if it had been. So if negative x to the 21st plus y to the 14th, then that would have been an expression, a binomial now, in two variables, and now the degree of that binomial would be 21, because I was adding the x term to a y term, which is different than the product of an x factor and a y factor to appropriate exponents. I'm having trouble articulating that carefully.
So if you're adding then you go with the larger degree.
If you are adding the two variable parts, then it's simply the larger exponent is your degree.
Okay.
But if you are multiplying two factors, both involving a variable, then you have to add the exponents to get the degree.
Okay.
And that's a little bit in the same sense we're doing what? Adding exponents as we do these problems. Okay? Earlier, a couple of us were talking about being on the freeway and making plans for how long it's going to take you to get somewhere. And yesterday, I met one of my sons at a sort of place between the Bay Area and here, and so we were both in the traffic. Now, I was going against the traffic. This was at about 3:30 yesterday, 4:30. Take it at 4:30. Close to the rush hour. And I'm not sure how we define rush hour on the freeways now. I think it's any time you're on the freeway, nearly. But going against the traffic, coming back to the valley, my time was pretty good. I didn't have a lot of traffic that I was fighting. Darren was coming out of the Bay Area going with the traffic. And so his judgment was, okay, I'm going to need lots of time. So he gets off work early, and in essence, because he gets off work early enough, doesn't need nearly the time he planned for. So you get off work early at 3:30, get on the freeway immediately, and he's a half hour early. So you made all this plan for the extra time and didn't need it. Now, because it was necessary for us to finish up our obligations here at the college, Sarah was in a lab over in the other campus. I was doing some encoding of the video. We were late getting started and hit some traffic just up at the 580, 680. What I'm getting at is a form of Gumperson's law that goes with Murphy's law. If something can go wrong at will in your planning, when is it most likely to go wrong? When you least can afford to have it. It's inverse probability. So he leaves early, doesn't need to worry, plans for it, and then there's no problem. I leave late, not wanting it, and that's when most likely what's going to happen. Somebody's going to get stalled on the freeway, and you're later than you wanted. We thought we could do it in 45 minutes, and it took an hour nearly. That's Gumperson's law. Now, what does that have to do with these problems? The more steps in the problem, what's more likely to happen? A mistake. Because you're doing so many of them. You do enough repetitions of anything, and eventually there's a hiccup. So you write more steps so you feel more comfortable and then have a greater likelihood of making the mistake when you were trying to be more careful. That's sort of a perverse version of Murphy's law. You do more steps so you won't make the mistakes, but because you've done more steps, it's more likely you will get tricked somewhere. And all it takes is one error and 5, 6 lines of output blown. Any of you doing programming understand that totally. Write 6 pages of code, and all it takes is one parenthesis out of place, one small little symbol that shouldn't be there, nothing works. That's very frustrating. It's one of the reasons I didn't stay in programming or computers. It just seemed ridiculous to fight syntax and spend hours and hours in a lab in those days where you didn't have corrections you could make on the fly. It meant you redid the cards and you submitted 90 or 100 IBM cards, rubber banded together, dropped them off at the computer room. It'll be batch processed later. Come back at midnight, 3 a.m., and then if it still doesn't work, change another card, resubmit. Okay, it was the abyss. It's interesting, just occurred to me, computers are still an abyss. You can sink more time into them than you ever dreamed possible. Just a little different perspective. You can do it now on the fly and get frustrated more quickly. Okay, any questions in the process here before I go back to the book and we look at the problems you're going to be dealing with as you are going to have fun with this? Okay, no fun, no fun. You don't want fun. Be gentle Go gentle into the night. Is that what I'm hearing? Okay. Page 239. Let's just look at the kind of problems that are there just to get an overview. Okay, we're on 239. Here's 29. What's the trick here to be careful of? The negative signs. Be careful, okay? And then 35, same problem with those negative signs. Coming off there, obviously life's going to get more interesting. So we go to page 241. And it just, at some point, I'm sure it seems like overload. The more factors in the expression, it seems like somebody's just playing with your head. And again, in 72, the 5 to the first would be a good little step to put in there. But on these problems, the question, okay, I'm going to use as an analogy here. Do you remember doing long division as a kid? And the first few long divisions weren't too bad as long as the divisor was 1 or 2 digits. And then it seemed like the authors of a book had to get 4-digit divisors just because they were there. And then it quit being fun. Well, in a sense, you may have the feeling, okay, we're just playing with your head. We're just going to give you a lot more factors, a lot more symbols, seeing if we can push you over the edge. But from a practical point of view, you are going to experience, as you use this language to do more sophisticated things, you're going to need to see expressions not all that different from what we're seeing on this problem 75 again, coming back to that problem. So it's not just a matter of trying to play with your head. Get into the spirit of it. See it maybe, can you do these and get fast with them, and can you make easy transitions from the original problem, one intermediate step and an answer. At the beginning, run the detail, but then try to get a little bit more comfortable with what's there. Let's look at number 80. Now we look at what? A mess in the numerator, something not too bad in the denominator, but to the 4th power. And notice the caveat, z not equal to 0. I hope as you see something like that, you have a mental impression of what you're going to do. Well, let's turn the page again. Unfortunately, there's nothing there. It's exciting, except a problem about interest that you would have on a loan with compound interest. So nothing much exciting there. What is missing as we come off there is a whole bunch of problems like 79 and 80. Folks, you've been cheated. Let's look at 79. Only 2 problems involving fractions. That's not fair. There should have been 20 like that. I mean, I feel disillusioned at this point. Yes, we should go back and resubmit the book and say, I want another 20 good problems. However, do not despair. If you take intermediate algebra, you can see more of those. Okay, so that's what would characterize intermediate algebra. The book used to be a little more demanding for 70. And what's happened is 90's become a little less demanding than it used to be. So we've skimmed a little bit off of 70, put it into 90, taken some of 90 and put it into a 121 and 122, and made what was supposed to be a 2-semester offering 2 years. So that's the trade-off. I'm disappointed in that, but you probably aren't. The question, where are we going next? This is the advanced organizer. We've had polynomials. What would be more fun than to multiply polynomials together? We are going to really have fun tomorrow. And I want you to think of cheerleading. That is what we're going to do tomorrow as we do some things with polynomials. We're going to practice some cheerleading. So with that as a kind of lead-in, for those of you who have seen anything with algebra before, there's a little acronym. I'm going to remind you of this acronym. I've got that too tight in the focus. Okay, let's try that, Debbie. FOIL. Now, I don't know if you remember anything about FOIL. FOIL stands for first, outer, inner, last. Okay, so first, outer, inner, last. And that's what we're going to talk about tomorrow with cheerleading. Think how cheerleading and FOIL go together. So that's where we're headed. Your homework assignment, because we need to wrap this up momentarily. And so let's see what we can do to make this enjoyable. There's nothing particularly exciting about any of these problems, 1 through 80. I certainly want you to skip the what? The calculator problems. Skip the even and the odds. I heard that. Okay, so I think we might as well just shoot for the moon here. 1 through 80 odd, and exclude the calculator problems. And it's just the repetition. You need a lot of repetition here. I think doing 40 problems or less, it's more like 35, I think, probably is going to be about what we need, and hopefully it'll go smoothly. So, Debbie, what are we going to close on?
Do it till you're satisfied.
And what's the group still drink?
BT Express.
BT Express. Do it until you're satisfied. Lots of algebra. Have a great morning.